Thank you so much for joining. So today is day two of our MMT seminar series. This is our intermediate 2026 thing, so we'll get started in about 10 minutes. So our rough schedule here is from this is being a little weird. Let me reload. So our rough schedule is going to be from 2:10 to 3:10. We'll be working through a few problems. Um, and then at 3:10 to 2:10, we're going to have a very brief break because that's going to be a lot of problem solving. And at 3:20 to 4, we're going to solve a few more problems. So when this says intermediate, this really just means around late AMC 8 to mid AMC 10. With a few problems of that are a little bit harder than that. Yeah, so 1 hour and 50 minutes. So from there, we are going to wait around 6 more minutes for a few more people to join. So the general structure of this is we're going to go over, we're going to present a problem. I'm going to highlight something in red because I do believe that interaction is really important. And then that's going to be a question for you all, like what theorem should we use? Or like do you have any thoughts on how to strike this problem? And then we can work through it. And we'll get to the solutions. So at any point in time, feel free to ask questions in the chat, ask for hints. Our so Gavin is here, who's also the Sting Math staff. If you would prefer private chat, and that's completely okay, feel free to send private chat messages to him as well. So with that, we'll get started in around 5 minutes, and thank you so much for joining. I really appreciate it. So I think we're about good to start. So, as a quick introduction, I'm Margaret. I'm a homeschooled high school student, and I've qualified for AIME, and my favorite competition is the USA Mathematical Talent Search because I really enjoy um, having a extended period of time to solve problems and then giving proof solutions to those problems because it I I do enjoy being able to spend longer amounts of time on things. Um, Gavin is switching to his computer only, so he should
Um,
be here.
yeah, I switched to my computer.
Okay, awesome. Oh, and also, sorry if I sound a little bit weird. I'm still recovering from a cold. Okay, so from here, I think we're okay to get started. So here's our first problem. If we let m and n be positive integers, Albert calculates the quantity 1 plus 2 plus 3 plus so on and so forth up to n, and Betty calculates the quantity 5 plus 6 plus 7 all the way up to m. So given that Albert and Betty get the same sum, what is this sum? So how can we add up all of these numbers over here? Because we know that A and B are going to get the same sum. Yeah, Lizzie, go ahead.
So we could like use the formula for adding consecutive integers. So, wait, so you said the Albert sum is A? Okay, so n plus 1 times n divided by 2 is equal to 5 plus m times m minus 4 over 2. And I don't think that we should solve the equation. And then we could maybe like try a few values of them.
Was this what you said? I didn't quite
Yeah.
catch what you get for the M.
So if you multiply it by 2 on both sides, like if we multiply it by 2 on both sides, then we know like m squared plus 5m is equal to n squared plus n. And I think that like now we can just try some values of m and n.
So that is a really great start, and yeah, you absolutely summed up the N side correctly. So, but what we can do here for the um M and N sides, like there is a really nice factoring trick that we can use a little bit down the line. But real quick, if we backtrack a little bit, you're absolutely right with the n and n plus one divided by two part. But one thing that we can do is, yeah, check how many numbers are in the second sum. So notice how we start at 5 here and then go to n. Um, because of that, we can actually write this as m plus 1 over 2, and then add 10 to this side over here. And we get 10 plus, we get 10 because we have 1 plus 2 plus 3 plus 4. So yeah, and then from there, you're absolutely on the right track. If we simplify all this by multiplying by 2, we end up getting n squared plus n plus 20 is equal to m squared plus m, and then all of a sudden this becomes a lot easier to deal with because we end up getting 20 is equal to m squared minus n squared plus m minus n. So does this pattern look familiar to anyone? Because there is a really cool way to factor this. Yeah, let's go ahead.
I'm pretty sure that like we're gonna use that m squared minus n squared is m minus n times m plus n.
Yeah,
And, and
absolutely.
then so the m minus n times m plus n plus m minus n times 1 is equal to m minus n times m plus n plus 1.
Yep. So we have
And
20.
then that's equal to 20. Um, and then I'm pretty sure that like we try some values later.
Yeah, so let's try some values. So we know that, so
Like
we
my
could go
idea
ahead.
is to like say like maybe try the first one is 5, the second one is 4, and then solve that for m and n. Like that's my proposed way to do it.
We could absolutely plug in m is equal to 5 and n is equal to 4. That's what you were proposing?
No, I'm proposing that like the things in the first parenthesis is 5 and the
Oh,
second
I see.
parenthesis is 4.
Yeah, okay, so we can check and see what values make that work. So we have m minus n is equal to 5 and m plus n is equal to plus 1 is equal to 4.
And
In
that's
other,
not possible. That's
um,
not possible, so I think it has to be like 2 and 10.
Possibly. So if you try 2 and 10, you'll also realize that isn't possible because m minus n and m plus n plus 1, they can't both be even. Um, so what's another pair that you could try?
1 and 20? I don't know.
Yeah, 120 is one that we could try. Um, so what is a way that you think,
If m is 10 and n is 9.
yeah, so if m is 10 and n is 9, then it works out with 1 times 20. And then we know that, and then all we need to do is sum up one of these. So let's take n because it's an easier sum to do.
So 1 added all the way to 10 is 55. So yeah.
Really close. We're only adding it up to 9.
Oh, okay, then it's 45.
Yeah, 45. Yep. And you can see they did the exact same thing we did, factoring over here. Um, Opposite parity, meaning that the only valid factorizations are 1 and 20 and 4 and 5. Um, and then that's how we know it has to be 1 and 20 because otherwise n would be equal to 0. So quick check of okay, so with our next problem, we have let a, b, c, d be a square. So the first thing we want to do in any geometry problem is to draw a diagram. If the largest circle that can fit inside this square, so it's going to look something like this, has an area of 2023 pi, then what is the area of ABCD? So first of all, what's something is it 8092? Let me really quickly check. Um, yes, it is. May I ask how you got that though?
Wait, can I talk?
Yeah, go ahead.
Okay, so since the area of the circle is 2023 pi, that means that pi r squared is equal to 2023 pi. So r squared is 2023, and we don't need to simplify that anymore. Now what we want to find the area of is 4r squared. So 4 times r squared is just 8092.
That's a really clever way to solve it. Yeah, so that is indeed the answer, 8092. Yeah, and also for anyone confused about why we have 4r squared being the area of the square, it's because if r is like this length over here, then 2r would be this length over here, and then you would end up multiplying 2r by 2r to get the area of the square, which is equal to 4r squared. Okay, awesome. So just really quick, does anyone have any questions about that one? Okay, and feel free to send questions anytime in the chat, even if we're on a different problem. And yeah, so they can tell, you can see that they did the same thing you all did over here. And honestly, great job for solving that one so fast. So, oh, now we've got an interesting number theory at once. So what is the smallest positive integer, let's call this a, that cannot be expressed as the difference between two prime numbers? So, what is everyone's thoughts though on this one? Or wait, no. Or, I mean, we can try 4, but that would be same as 7 times 3, so unfortunately not.
No.
Yeah, go ahead.
7.
Awesome. So how did you reach that conclusion?
I kind of just started trying like all the odd all the like numbers. I just started from 1, yeah. And then 1 can be 3 minus 2. 2 can be 7 minus 5. And 3 can be 5 minus 2. 4 can be 11 minus 7, yeah. And 5 can be 7 minus 2. 6 can be 13 minus 7. Uh, and 7 can't really be anything.
Yeah, awesome. And 7 is the answer. So yeah, great job. So with that,
I will launch the pacing poll.
just want to know how we're doing. If we're going too fast, too slow. So yeah, it would be much appreciated if you could take a couple seconds to answer that. Um, so thank you so much for everyone who answered. It looks like we're going at a more or less good pace. Maybe we can go a little bit faster. Um, Generally speaking, it looks like we can go on with um, more practice. Also, to the one person who said they can teach the class, that's awesome. You can absolutely volunteer for Mustang Math at some point. Um, and are you comfortable in class? Looks like generally yes. If you don't feel as comfortable, absolutely feel free to private message, like send private messages if that's more comfortable for you. Whatever works best. So with that, we can go ahead and move on. So there are 15 Mustangs in a stable, 5 blue, 5 green, and 5 black. Yuki and Anna each pick a different Mustang at random. So what is the probability that they choose Mustangs of different colors?
Is it 5 out of 7?
Um, Let me actually check that. Yes, it is indeed. So, all right. But how did you solve that if you don't want to explain it?
Because if one person chooses one Mustang, then the ones that could be different colors will always be 10. And then since without replacement, because they each pick a different Mustang, then that would be over 14 and simplify it to 5 out of 7.
Awesome. Yeah, so because they're all the same numbers, regardless of what the first person picks, there will always be 4, 5, and 5 left. Then there will only be 2 groups of 5 that the other person can choose from. So yeah, you can see that's exactly what they did here. So on this next one, it said, let floor of x denote the greatest integer less than or equal to x. So for anyone who isn't familiar, it's like rounding down. So for example, like floor 3.2 is equal to 3. Floor 3.9 is also equal to 3. Because it's the greatest integer less than or equal to x, just rounding down no matter what the decimal is. So here it's asking us to evaluate this list over here, where we have 10 over every single integer between 10 and -10. So they didn't include 0 for obvious reasons, because you can't really divide by 0. But how do you think you could go about solving this? Because you can see that this first integer would absolutely be 1, and 1 floor 1 is just 1. But then 10 floor 9 is 1.111, so on and so forth. That's also going to be 1. But then it gets a little bit weird because if you go over to 10 floor 1, that's going to be 10. So you could absolutely go ahead and like solve each one individually. It wouldn't be like too much work. Um, but what sort of other approach could you take to this one? Perhaps grouping terms, because grouping is a really great way to solve problems with a lot of sums like this. Yeah, go ahead.
You could like group it you could group 10 over 10 over 10, 10 over 9, and then all the way to 10 over 6, and those would be all equal to 1. And then from 10 over 5, and then 10 over 4, there would be 2. And then 10 over 3 would be 3. And then 10 over 2 would be 5. And 10 over 1 would be 10.
Yeah, absolutely. So that is one way we could do it. So as you said, we end up getting, 1, 1, 1, and so on and so forth. Few numbers in there, and then 10. What about the negative terms? Like, what would happen to those?
Um, you could just like solve it, I guess.
Yeah, sure. So we could do that. So 10 over negative 10, we know that's going to be floor of negative 1. That is just negative 1. Now, the interesting thing here is that the floor of 10 over negative 9 is negative 1 point, and then so on and so forth. But because flooring is the greatest integer less than or equal to x, you notice that negative 2 is actually going to be how this is floored. So that sort of brings up a really interesting pattern. And so sorry, I'm going to need to erase this to give us some more space. So we can sort of group the terms as like say, and we can denote whatever number we have as a. So if we have a and negative a, we can kind of group these together. And as you can see, if x is, or sorry, not x, um, if if a ends up being an integer, then flooring a and adding it to negative a is just going to be equal to 0 because you can see, as in this example of 10 over negative 10 and 10 over 10, it'll go to an exact value. So flooring it doesn't make a difference. You add those together, you get 0. But if a is not an integer, then, and you can see that these negative values will round to the next negative number down because that is the greatest integer that's less than or equal to that number. So if it's not an integer, we end up getting negative 1 instead. So one thing we can do here is group all of these terms symmetrically. So 10 to its negative counterpart, 10 over 9 to its negative counterpart, and so on and so forth. And then figure out what terms are integers. So what terms are integers and what terms aren't. And then from there, we just count negative 1 for all the terms that aren't, and count 0 for all the terms that are integers. So among 10 over 10, 10 over 9, 10 over 8, and so on, which of these are integers? Yeah, so we get 10 over 10, which is 1, 10 over 5, which is 2, 10 over 2, which is 5, and 10 over 1, which is 10. So out of our 10 terms on this side, we have 4 non-integers. So that means that there must be 6 on this side, meaning our answer will be 6 times negative 1, which is negative 6. So I just want to say if you see this on a competition, you can absolutely add it up by hand. That would be a good short-term solution, but learning short or methods like these can help you when these problems become more complicated. So yeah, you can see over here, it might not be too intuitive to think about grouping these terms at first, but just in general, grouping is what you want to do when you see really large sums like this. Okay, so next we have Sebastian with a few, or with matching outfits where they consist of a hat, pants, shirt, and a pair of socks. So I'm just going to put the shirt as SH. Um, oh, awesome, Gavin. Honestly, they might have adapted it for this seminar because they'll sometimes adapt competition problems for these. So he has four of these sets in colors of red, blue, green, and yellow. If he randomly picks a hat, pants, shirt, and pair of socks out of his drawer, what is the expected number of matching pairs of clothing pulled? So, who here knows what an expected number or expected value is? Yeah, go ahead.
Expected value or numbers like is like the average number of matching pairs on all of the tries.
Yeah, so like if you were to eyeball it, like how like what would be the average like you would get? So, for example, if you were to flip a coin, say 100 times with an even chance of heads or tails, you would expect there to be around 50 heads and around 50 tails. So from here, um, we have, oh, no, if he pulls out an entire outfit items of the same color, then you would have matching pairs of clothing. Oh, yeah, we're getting a little bit of disagreement over the answer. So yeah, let's go over this together. So, oh, a lot of disagreement. Okay, three different answers. So this is interesting. So between so let's say you picked out one item of clothing first. So regardless of what color that item ended up being, there's a 1/4 chance that the second item is going to be the same color. So if say you picked red, the second item would have a quarter chance that it would also be red. So in other words, you take any two items, there's going to be a quarter chance that they're the same. So let's first of all, what is the number of like total pairs of clothing? In other words, what is six or four choose two? So just quickly checking, is there anyone who doesn't know how the choose function works? Okay, so um I'm just going to assume that you do, if you Google it, you'll end up looking at this absolutely horrendous looking function, but it's all right. It's a lot simpler than that, trust me. So this is going to be 4 times 3 over 2 times 1, because and then we end up getting these two cancel out, which is just 2 times 3, which is 6. So out of all of these different combinations, there are 6 ways, or there are 6 pairs of clothing that you can pick. And out of those 6 pairs, 1/4 of them are going to be the same color. So out of all of this, that means we would have 6/4, which is the same as 3/2. So yeah, and I can absolutely see how some people get 1/64 if you ended up trying to get an entire outfit of the same color. Um, yeah, linearity of expectation. It's a really cool thing. It comes, it's very, very handy when you get to higher level combinatorics and probability and all that. And yeah, so just real quick, there's a really concise solution over here. So out of all the different, because they're asking like how many matching pairs of clothing, what is the expected number? So whenever you have expected number, you can use linearity of expectation, find all the matching pairs, and then multiply by the probability. Okay, so example 1.7, if a of n is equal to -1 to the power of n plus 1/2 for all integers n, they want us to evaluate the following sum. So this one does look a little difficult because we have a lot of terms over here. But how do you think we could, well, what would the first few terms look like? Yeah, go ahead.
So the first term is 1 times -1 to the power of 1, which is equal to -1. So the first term is -1. And then the second term is it's -2. And the third term is -3. And the fourth term is actually 4. It's like positive for this one. And then I think like the fifth, sixth, and seventh term are all negative, and the eighth term is positive. And then the ninth, 10th, 11th terms are negative, and the 12th term is positive. Like I think that like the numbers that are multiples of 4, they're positive.
Yeah. So, and that's going to take a little while to write out here. But yes, this pattern does repeat with modulo 4. So let's try to see what the pattern over here is. So you saw like for a 1, the exponent over here is just going to be 1. For a of 2, this exponent over here is going to be 2 times 2 plus 1/2, which is 3. And then we can sort of look at that pattern specifically with the exponent. It, as you, if you were to take it like mod 4, then you can see a really cool pattern. So, for example, like, actually, let me write this out on a separate part page. N times n plus 1/2. So it repeats modulo 4 because if n is congruent to 0 mod 4, then all of this is going to be 0 mod 2. Or this entire exponent is congruent to 0 mod 2. If n is congruent to 1 mod 4, then you end up getting it congruent to 1 mod 2. Here, I'm just going to write this 0, 1. And then if, no, case 0 would be up here, this one. So if n is congruent to 2 mod 4, then our exponent is again congruent to 1 mod 2. And if n is congruent to 3 mod 4, then our exponent is congruent to 0 mod 2. So that is really good. And so we can end up, so what sort of like rule can we make out of this entire pattern? Because you might see that this exponent fluctuates between 1 and -1. Oh, what is the problem again? Yeah, it's up here. I'll try not to scroll down too much. So if you end up solving these exponents, yeah, it looks like a lot of people are getting this one. It is so if you take this mod 4, you can see that if a so we know a of n is equal to -1 if n is congruent to 1 or 2 mod 4. Likewise, that's in other words, that just means that this exponent is going to be like odd. Now, a of n is equal to +1 if n is congruent to 0 or 3 mod 4. In other words, a is positive or even. So then we can, and sorry, I'm going to need to scroll down a little bit. We can split it into terms of every 4 consecutive numbers. So we can group 1 times a of 1 plus 2 times a of 2 plus 3 times a of 3 plus 4 times a of 4. That's 4 terms. And solving all this, we know that 2 of these are going to evaluate to -1, and the other 2 are going to evaluate to 1. We add all those together, we end up getting 4. We solve this the same thing for 5a times 5 plus 6 times a of 6 plus 7 times a of 7 plus 8 times a of 8. I'm sorry, this is a lot to write out. You can see that this also evaluates to 4, so on and so on and so on. And you can see it's done over here, and I just sort of ran out of room to write. But we split it into 505 sums, each summing to 4. 505 sums times 4, meaning the total is 2020. So yeah, this problem looked kind of impossible at first because we have this function and we don't really know how to evaluate it. But they're always, like, whenever you have large sums, you can pair numbers together. So here we are pairing them in blocks of 4 instead. Okay, now moving on, we have a quadrilateral ABCD is constructed such that BD bisects ABC. So we want X to denote the intersection of AC and BD. We have that AB is equal to 4, BC is equal to 8, AC is equal to 6 square root 2, and we have 2 congruent sides, which is really nice. So we want to find CD squared. So let's try to draw a diagram. That's the first thing we want to do. So let's draw an arbitrary quadrilateral, ABCD, and then we can always fix our diagram later if it doesn't end up looking right. So we want BD to bisect ABC. Oh, that doesn't look right. Diagram not to scale. And we want X to denote the intersection of AC and BD. So the intersection of its diagonals. We have AB is equal to 4, BC is equal to 8, AC is total diagonal over here, 6 square root 2, and BX equaling XD. Okay, diagram really not to scale in this case. Equaling 4. And we want to find CD this side over here, but squared. So in this case, I'll draw a better diagram, but what ideas could you have to solve this problem? And whenever we have a lot of side lengths like this, it is a really good idea to, especially with angle bisectors, it's a really good idea to look for similar triangles. If angle bisector, then log cosines. So you can absolutely try that. Yeah, you could. But there is a way with similar triangles that were that I'd rather take for this one. So with similar triangles, we have ABX over here being similar to DVC, and that's the first key thing that can be kind of difficult to see at first. So with that, like we know that that's true because of the AB equals BX equals 4 part. Because notice like AB and BX are also, they're all 4. And then also we have that angle bisector over there. So they're going to be similar. Now, okay, let me write that on the side so we don't end up mixing this up. So we end up getting triangle ABX is similar to triangle DVC. So there are another pair of similar triangles that we can find specifically, and I'm going to mark this one in green, BCD. And CDX. So we know BCD is similar to CDX. So now we have a number of congruent triangles. And that means that we're going to have a lot of same angles over here. So what conclusions can we draw from that? We want to do a lot with fractions with involving sides for this problem. Here, let me this to clear up space. So it does look like some of you already found the answer. So I'm going to go ahead and go through this problem. So specifically, because of all of these similar triangles, we know that angle BAX is equal to angle BXA, which is equal to angle BDC, which is equal to angle BCD. So now we can use all of our, and you can use this to show that like these triangles are similar. So now we can write a few like side ratios and then use that. So specifically because of these, we know that CD over XD is equal to BC over CD. And this is really good because it includes CD, our unknown. So here we just multiply to get CD squared, which is really nice, equaling XD times BC, which is just equal to 8 times 4, which is 32. So yeah, it can be really difficult to get those similar triangles, but yeah, you can absolutely solve this using the law of cosines. That works too. Their solution is a little long-winded, I gotta say. Like it does give a really thorough explanation of how they end up getting the similar triangles they showed. But there are a lot of like I would say a lot of this sort of comes with the similar triangles part. Okay, I think we can get in one more problem before taking a break because we've got because we've gotten through quite a bit of this handout. So John throws a ball up in the air from a certain height. If it peaks at 2 seconds at an altitude of 37 feet, and it's good to sort of do this as a coordinate system, and lands after 6 seconds, what height was John at when he threw the ball to the nearest foot? This is actually the sort of problem you'd see in Navy physics, but yeah, might as well do it in competitive math. So, um, what is everyone's, so what's your thought process with starting this one? Convert to vertex form. Yeah, that is a good idea. So we have two coordinates, 2,37, and also just to clarify, they mean lands after 6 seconds, as in one of the zeros is 6,0, not 6 seconds after the 2 seconds. So we have two coordinates, and we want to know this first coordinate over here, where Joan was. Or not this first coordinate, apologies, where the height is at t is equal to 0. Yeah, so 28. Yeah, so let's go over how we got that now. So if we want to write this in so we could write it in factored form. We could also try writing it in um, vertex form. So here, so first of all, we might want to know like where is the zero, the other zero over here, because that's some really useful information we can figure out. So because zeros are symmetric around the vertex, because this 0 is 4 away from 2, we know that this also has to be 4 away, meaning this is at -2. So that's really useful because now we have oh, now we have y of t equaling a x plus or t plus 2 t minus 6. And this a is different from this a, to be clear, so let me replace this with a different variable. Let's call it, I don't know, d or something. So from here we can plug in the other point that we have, 2,37. So we end up getting 37 is equal to d, 2 plus 2, 2 minus 6. So that's going to be 4 times -4 times d is equal to 37, meaning our coefficient d is just going to be -37 over 16. So that might seem a little intimidating to deal with at first, or not intimidating, but just a little inconvenient because that's not a really great fraction to be looking at. But now all we need to do is plug in 0 for t, because that's what we're trying to find over here, this x value, and then we're done. So we have -37 over 16 is equal to 0 plus 2 times 0 minus 6. So solving this, we end up getting -37 over 16 times 2 times -6, and all of that will boil down to 111 over 4. So you might notice that they end up asking for like the nearest foot over here. So this ends up rounding to, let's see, 25, 60, yeah, 28 feet. So yeah, with that, it is around time for a break. So we'll see everyone back here at 3:14. So yeah, thank you so much for yeah, thanks so much for sticking around and interacting. I really appreciate the amount everyone is like participating in the chat and also through microphone. Oh, and coincidentally, 3:14 is the first few digits of pi. And also, yesterday was Pi Day. Anyway, that's enough about pi. Thank you so much. And now it's time for the break. So some time to take a short break, maybe move around, grab some water. I think we're ready to move on to the next problem. So, an adventurous Mustang begins at the bottom left of the shown grid. The Mustang can only move up and to the right along the shown lines. How many different paths can the Mustang take to the top right corner? So they can only move up and to the right. Maybe up a little bit more, to the right a little bit more. But they cannot pass or get into this very specific coordinate over here. So one handy thing to look at is, say this grid was actually filled in, this X wasn't here, we could pass through this point. How many total ways could we end up getting to this complement? I mean, you could do it that way, but in this case, there are, well, yeah, we can do it that way. So let's try to count the ways that we don't want and subtract them from the total. So we want total minus the ways that count this coordinate, which is 3, 3. So if the grid is fully filled, what is the total? So you'll notice that because the Mustang can only move up or to the right, there are 1, 2, 3, 4, 5, 6 different times that they need to move up and 6 different times that they need to move to the right. So that means that out of 12 total choices, 6 of them needs to be to the left, and 6 of them needs to be, or sorry, to the right, and 6 of them needs to be up. So let's choose the 6 to be up just arbitrarily. So we end up getting 12 times 11 times 10 times 9 times 8 times 7 over 6 times 5 times 4 times 3 times 2. 6 times 2 is 12, so that cancels. 5 and 2 is 10, so that cancels. We end up having a 2 and a 3 left. A 3 can cancel out with the 9. So, and the 2 can cancel out with the 8. So we end up having 3 times 4 times 7 times 11. So all of that together, and you could take time doing the multiplication, but because I did this problem beforehand, just trust me when I say that it is 324. Or 924, apologies. So what this is saying is there's 12 moves total, and 6 of them are going to be up, and 6 of them are going to be to the right. Yeah, awesome. So it is 560. So, but how did you get there, if I may ask? Like, how specifically would you count the ways that we need to take away? So let's do the same process, except counting the ways that we go through 3, 3. So we want to count the ways that you just path counted with the grid. Yeah, fair. That is another way you could that is a way you could solve this problem. So if we count the number of ways that we can go from 0, 0 to 3, 3, we end up getting 6, choose 3. Same logic as earlier, but like with this section of the grid now. And there are, in turn, 6, choose 3 ways to go from 3, 3 to 6, 6. But all of that, so we just end up squaring this. So we end up getting all this squared. 6 times 5 times 4 over 3 times 2. We end up getting 20 squared, which is 400. Next, we do need to account for the paths that like travel through this diagonal, but end up going up this point and span from 2, 2 to 4, 4 instead. So let's count over here. We want to get the paths that go from 2, 2 to 4, 4 and add those. So there are 4 choose 2 ways to do this, same logic as with the previous parts, which is going to be, or 4 choose, and then 4 choose 2 ways to go from here to 6 choose 6. So total that is going to be 6 squared, which is just 4 times 3 divided by 2, and then you square that, which is 36. So total, we end up getting 924 minus 400 plus 36. That is equal to 524 plus 36, which is 560 paths. So yes, you were absolutely right with the 560. You can, yeah, absolutely path count. Take away the counts we don't want. Either way, it completely works. So from here, yeah, and you can see they edited the way they did it. They wanted to account for paths that travel through the diagonal that spans from 2, 2 to 4, 4, this bit over here. And so yeah, take away the ways you don't want, add 36, and then you're done. So Carrie is sending out 5 invitations for her retirement party. Unfortunately, she hasn't gotten much sleep recently. Oh, okay. But randomly places each invitation in one of her 5 addressed envelopes. What is the expected number of invitees who will receive the correct invitation? Okay, so you have 5 invitations and 5 envelopes that are all distinct. And we want the expected number. So let's think about this. So for the first invitation, we know that can go in any one of the like 5 envelopes randomly. There are 5 different ways you could do it. That's like 1/5. 1. Yeah, that is honestly, yeah, that's right. So each invite has kind of a 1/5 chance of being correct, and then there are 5 of those. So yes, expected number is that simple. Each envelope has a 1/5 chance of being matched with the correct invitation, and then that is just 1. So you could sort of use this logic to expand it to any number of like correct invitations, honestly. So yeah, you don't want to be randomly placing invitations. That's not going to work out. Okay. So here we have find the sum of all positive integers n such that n squared plus 1 is divisible by n plus 1. Um, This one was Mustang Math 2024. I was wondering how you got it so fast. Okay, so yeah, so we just want the um GCD of n squared plus 1 and n plus 1 to equal the GCD of n plus 1 and n minus 1. And honestly, this uses the Euclidean algorithm, which I'm not sure why that was. I will say the tournament is kind of really hard for the grade levels it targets. But yeah, you because of this, we know that n plus 1 equals 2. Therefore, n equals 1, and the sum of all solutions is 1. So yeah, I don't exactly know how they'd expect like middle school students to know the Euclidean algorithm, but it's a really hard tournament. But yeah, honestly, good job for recognizing it. Rewrite it, yeah. So yeah, dividing polynomials. Fair enough. I mean, I don't know. I'm in a school where nobody except me does competitive math, so maybe it's just me. Anyway, if 856, 857 A6 is divisible by both 3 and 8 for some digit A, what is A? So you can absolutely solve this using long division. Um, yeah, wow, you guys are really fast at solving these. Was this one also an MMT or something? Yeah, so if it's divisible by 3, then that means 8 plus 5 plus 7 plus A plus 6 is also divisible by 3, which is the same thing as which means like A could be either 1, 4, or 7. Yeah, and then do the same one for 4. That means that 7A6 must be the one that you can use that you can divide by 4. So our only options are 716, 746, and 776. And then if you were to try dividing all these, it might take a bit longer to do this, but yeah, you can just cross these off and get that our answer A is 7. Go ahead.
For the dividing trick for 4, is it the last 3 digits or 2?
Um, last last 2, but last 3 works too. Works as well. Yeah, 3 for 8. But 8 is the same thing as 2 times 4, which is kind of intuition is like why that works. Yeah, 4 divides into 100, which is why you take the first 2 digits, and 8 divides into 1000, which is why you take the first 3 digits for that. So yeah, the same here, and yeah, that's that probably. So square side length 5. Oh, this is nice. We haven't seen geometry in a little bit. It's cut into 4 identical quadrilaterals and a unit square. Okay, so not uniform. Um, such that the 4 quadrilaterals can be moved and rotated to form a new square. What is the sum of the smallest and largest side lengths of one of the quadrilaterals? So we want it in simplest radical form. So if we have a unit square and 4 identical quadrilaterals, you can try like go ahead and try different organizations and like cut like different ways to cut the square up and see how that goes. So instead of, so if you're trying this, you might see that finding the some of the smallest and largest side lengths might be a little bit difficult because you'll need to find what the quadrilateral looks like in the first place. So instead, we can sort of think of this more abstractly in terms of like our total area, which is 25, and then how much we take away from that. So first of all, we have -1 from the unit square, leaving us with 24. Um, and so we know that um, each of this 6 almost. We want the I mean, yeah, I think you're on the right track somewhat. So if our new square has area of 24, then what will its new side length be? Yeah, so square root 24, and we can simplify that into 2 square root 6. So because so we know that the sum of the smallest and largest sides of the quadrilateral must be that. They have a kind of better explanation down here compared to what I scribbled up here. The area of the original square is 25. You remove that, that's how much area there is. And so the area of the new square has area 24. So with that, when we can move on to the next problem. So when 47 and 73 are divided by a positive integer n, they produce the same remainders. They're asking for how many possible n values of n are there. So we can start out by writing this. So we could start out with modular arithmetic. There is a way to do that. That might be a little bit more complex, but remember, when the difference of two numbers is also divisible by n, if the two numbers have the same remainder in the first place. Here, it's going to be a bit of a pain to write out, so let's not do that. Oh, okay, so there's a little bit of disagreement, 4 versus 3. So let's perform this subtraction and find out. So 73 minus 47 is 6. And from there, we can just count out the divisors, 26. So we end up getting, 1, of course. There's also 2 and 13. So yeah, that's just a 1, 2, 13, and then you can't forget 26 itself. So you can't have 1 because n is greater than 1 over here. So then we're left with just these, and you can count those up and get 3 different values. So yeah, you might have forgotten to discount the 1 because of this subtle thing over here. Okay, so if we have ABC, sorry, ABC is 90. Okay, they share A apparently, so let's draw this over here. So we have ABC, where let's say A is here, B is there, C is there. We know B is our 90-degree angle. And we have A, C, D, where C is our 90-degree angle. So if BAC is equal to CAD, AB is 20, AD is 23. We want the ratios of the areas. So yeah, it looks like a lot of people are getting 20 over 23. So let's go through that. So let's call A the ratio of their side lengths. We know that the ratios, so if A is the ratio of the corresponding side lengths, we know that's going to be A D over A C. So this one and that one, that's corresponding side lengths, the two diagonals. We also know that's going to be the same thing as AC over AB. Again, the same sides for the two similar triangles. So all we need to do is square this to find the ratio of the areas. So if we square this, we end up getting AD over AB, which is 23 over 20. So if the ratio of the areas of similar triangles, yeah, similar right triangles stays up here. Almost we don't need to square them. So because like all we need to do is multiply, so kind of what we did over here, like erase this. So we know that a squared, because a is simultaneously equal to ab over ac and ac over ab, we can multiply the two together. Sorry, I miswrote this. So we can multiply the two together to get the ACs to cancel and then get AD over AB, both of which we have the side lengths of, which is just 20 over 23. So notice how initially we didn't actually know some of these sides, namely AC, but by squaring it, we cancel it. So, or sorry, this is 23 over 20. So if we want but notice that we want the ratio of the area of ABC to ACD, so we actually want a 1 over a squared, so that's going to end up equaling 20 over 23. So with that, and yeah, you can see they did the same thing over here. I do wish they draw diagrams for these. They make problems a lot easier to visualize. So yeah, I know it's been like a lot of problem solving so far, but yeah, we've got 20 minutes left, so let's power through this. And we're making really good pace actually. We're at 36 pages out of 43. So a 6-digit number n, let's draw these slots for these, has the property that each digit, except for the rightmost two, so excluding these, is the product of the two digits to its right. So what is the largest possible value of n? So let's write this in terms of variables first of all. Let's say this is a1 and this is a2. That means that this is a2, a1. This is a2 squared a1. I'm just multiplying these two over here. Likewise, this slot will be these two multiplied. a2 cubed, a1 squared. And the slot will be these two multiplied. a2 to the fifth, a1 cubed. So because these are all single digits, if we look at this slot, we can immediately see that since we have something raised to the fifth power, you're sort of on the right track. It's not going to be 6 ones. I will say that though. You are right that a2 does have to be 1 because there's no way something raised to the fifth power can be 1. But if we so we're not a1 is not equal to 3, but you are sort of on you do have the right idea. So we know a2 must be equal to 1 because there's no way something raised to the fifth power is going to be less than 10. Now we do have a1 cubed must be less than 10. Now notice that if a1 is 2, that does work because 2 cubed is 8. Yeah, 2, no worries. So now all we need to do is, because a2 is 1, we just ignore those. So we end up having 1 times 8, which is 8. 1 cubed, which is 1, times 2 squared, which is 4. 1 squared, which is 1, times a1, which is just 2. a2 times a1, which is 2. a2, which is just 1, and then 2 again. So we have 8, 4, 2, 2, 1, 2. So that we have solved this problem. Now notice that technically 111 like satisfies the conditions, but we're looking for the largest possible value then, so it doesn't satisfy that particular criteria. Ooh, okay, so this is interesting. If O is the sum of all odd integers, and you'll see these problems on the AMCs a lot with O being the sum of all odd integers and E being the sum of all even integers. But so here they give the bound of 0 to 9999 inclusive. They want us to compute O plus E divided by O minus E. So you might notice that O plus E is just the sum of is like the sum of all numbers to 0 to 999 or 9999. So let's solve that. How could we figure out what this sum is? 9999. Wow, you are really fast at this. So let's first sum these together. We can use these sum formula for 0 plus 1 plus 2 plus so on and so forth up to 9999. That's going to be 9999 times 10000 over 2. We can just cancel this and turn this into 5,000. Now let's keep this like this because we don't really want to expand just yet. We want to cancel some numbers out. So now we just want to compute O minus E. So whenever we have large groups of sums like this, we want to group the numbers up because we know this is going to be equal to 9999, that's O, 9997, and so on. But E is going to subtract 9998 and 9996. So you compare all of these to get, oh, the odd is first. Yeah, isn't that what I wrote? So you can kind of pair these up. so that each of these end up equaling 1. Our last odd number is going to be a plus 1, and we can sort of count zeros even in this case. The parity of zero is widely debated, but doesn't really matter for this one because we're just adding nothing. So we end up getting pairs of 1, but we have 5,000 of these. So we have this equaling 5,000. So with that, with our numerator, we have 5,000 times 9999 over 5,000. Those cancel, and we are left with 9999. It's written out really nicely here. They paired the terms really well, and showed how all that works. And it's a bit more obvious when writing it this way that there are 5,000 pairs. Okay, so let's move on. In right triangle ABC with hypotenuse AC, point D lies on AB such that DC bisects angle C. So you got a median over here. Given DB is equal to 1, so each of these sides must be equal to 1 as well, and BC is equal to 2, we want to compute AC. That's that side over here. I'm actually going to highlight it in blue or red, doesn't matter. So how can we solve this one, do you think? I will say that, like, when we have a bisector like this, we can end up, well, there is a very specific theorem that we can use. What theorem can you think of that involves angle bisectors? Yeah, it's in the name actually. So we can use this to say that AC over AD is equal to BC over DB. You might see it written a little bit different occasionally, but the math will work out the same. So DB is 1, BC is 2. We know that these, therefore we know that AC over AD is equal to 2. And we know AC is equal to 2AD. And let AD equal X just to make this easier to figure out. Oh, I am sorry, these are not necessarily the same. Angle bisector does not mean total bisector. So if AD is equal to X, then we know AC must be equal to 2X. And then we can use a bit of algebra to figure this out. So, oh, and we know because DB is 1, we can write AB as X plus 1. So let's use the Pythagorean theorem to figure this out, because in ABC we have a hypotenuse and 2 sides. So we have X plus 1 squared plus 2 squared is equal to 2X squared. So if we solve this, we end up getting X squared plus 2X plus 1 plus 4. You know what, that's just 5 is equal to 4X squared. Let's solve this, we end up getting 3X squared minus 2X minus 5 is equal to 0. We can either factor this or use the quadratic formula. I'm going to factor this, so let's see. We can use a bit of grouping. Let's see, negative 15. Yeah, okay. We have 3X minus 5 and x plus 1 together like that. So from here, we can end up finding this. So x can't be -1. We know it can't be negative. Therefore, x must be equal to 5/3. Except because AC is equal to 2x, we know that AC must be equal to 10/3. So yeah, in short, we use the angle bisector theorem and then we algebra our way to the answer. Okay, is everyone all right to move on? Okay, I'm okay, awesome. So if so 4 people have a distinct number of coins from 1 to 4, and this is actually the last problem in the packet. Honestly, thank you everyone for like participating in the chat, and um, I really appreciate it. I was not expecting to get through all these. So 4 people have a distinct number of coins from 1 to 4. I'm just going to draw 4 stick people because it's entertaining. So if each person gives all of their coins to someone else in the group at random, what is the probability that no one ends up with the same number of coins they started with, expressed as the common fraction? So it might be a little bit difficult to count all the ways that no one ends up with the same number of coins they started with. So what we might want to use is complementary counting. So let's do this. What is the probability that cause someone to end up with the same number of coins? So let's say, and I'm just going to label these people 1, 2, 3, and 4. 4/27. Yeah, so that is the probability that people that like someone ends up with their original number. But there are different ways that this can happen if you go through the casework. So if so let's think about this. So if say person 1 and person 4 both give all their coins to person 2 or something like that, but person 2 gives their coins away, um, then like a situation like that, um, well, okay. So it's better if I write this out because it gets a little bit confusing explaining it aloud. So let's say person 1 and person 2 all give their coins to some other person, person 4, but person 3 gives their coins to someone else. So that has to end up, so therefore someone's going to end up with the same number of coins in this situation. So this happens with the probability of 1/3 times 1/3 times 2/3, because 3 can give their coins to either 1 or 2. And so we end up altogether with 2/27. Now there's another way this can happen. Say person 1 and person 4 give their coins to person 3, but like person 2 gives their coins to someone else. So same thing, we just sort of swap the people around a little bit. That also has a probability of 2/27. So altogether, that probability is 4/27. Now remember, this is the probability that the same that we have that's like somebody ends up with the same number of coins that they started with. So now but that's what we don't want. We actually want 1 minus this amount of cases. That's going to end up with the amount that no one ends up with their original number of coins. Yeah. So 23 over 27. Yeah, so hopefully that did help a little bit. They asked that no one ends up with the same number of coins they started with. That's going to be kind of impossible to count up, but it is possible to go through a couple of cases. They explain it really nice over here. They did kind of switch around the persons as the people as compared to what I did. But say person 1 and 2 both give their coins to person 1 and 2 give their coins to person 3, then but person 4 gives coins to say someone else, either one of them. That happens with 1/3 times a 1/3 times 2/3. But let's say person 1 and person 3 both give their coins to person 4, but person 2 gives their coins to someone else. So yeah, you're just sort of like swapping the people around, but the situation is still kind of the same. So yeah, that is the end of this massive 43-page packet. I truly did not expect to finish this at almost 4 p.m. on the dot, so I really, really appreciate everyone for sticking around. And I'm sure a lot of you are going to participate in MMT, but yeah, I would really encourage it. There's a lot of really interesting stuff that you can learn from those competitions. So yeah, I just want to say thank you. The recording will be posted as well as this entire handout. If you want to look through the explanations themselves. And I just really appreciate it. This has been one of the more active seminars in comparison to a few I've seen. So yeah, thanks so much for participating. So yeah, thank you. Yeah, thank you. Bye.